Hello, everyone, and welcome back. We are now talking about differential equations, but we're going to be solving for a particular solution now. So let's recall really quick what that means. So given a differential equation in the past, and by the past I mean just the last lesson or two, we'd say dy dx. Let's say we're given y equal, the rate of change is given by 2x. The derivative is 2x there. Well, then if we wanted to find the function y, you would write it as dy equals 2x dx, integrate both sides and say y is going to equal x squared plus c. So again, visually, what was happening here is if I denoted my dy dx in this color green, we have that the slope we know is represented by the function 2x. So there's my derivative function, dy dx. But the idea here is that y equals x squared plus c. Well, because of the plus c we don't really know what the exact answer is. There can be a lot of different functions y this derivative is talking about, right? So again, that means that there were infinitely many functions y such that the derivative of it was equal to 2x. So we're going to talk about a particular solution. So let's say we're given this problem, but let's say we know that of the function f of, say, at 1 or at 0, the curve is at, say, 3. Well, then what does that imply is that if we're at the point y equals x squared plus c, well, that means that we can solve for c, knowing that fact, and we can find that particular solution. So then we'd have 3 is equal to 0 squared plus c, which implies that 3 equals c. Thus, we know that for dy dx, and I'll just rewrite our whole problem here, equals 2x, and the f of 0 equals 3, with that information, then what we know is then the function y is going to equal x squared plus 3. And that's the particular solution to this differential equation. And I use the word particular just to match the book, but particular just means, the one solution, the solution to the problem, rather than there being infinitely many solutions. Okay. So let's look at another example where maybe our differential equation isn't in terms of x. Let's say, push this down a little bit. Let's say dy dx is in terms of y. Okay. Now, what's this graph look like? This might be a little bit harder to get. So what's dy dx look like? Well, that's what we're going to explore in the next video. And that's the idea of something called a slope field. Right. Where if you're not sure, we'll just write the slopes at every point. So slope field is basically the slopes or dy dx at every point. But again, that'll be next video. But that's okay. If we integrate this, we'd have dy over y equals dx. If we separate those variables. Integrating, we'd have the natural log, the absolute value of y is equal to x plus some constant c. Rewriting this as e to the x plus c equals the absolute value of y. And then we'd have y equals plus or minus e to the x, e to the c if I separate those right away, thus leaving me with some constant c, e to the x. Now let's say we also know in this problem, and I guess we could have set this up here, is that, and then we know that f of 0 is equal to 1. Well, let's not do 1. Let's do f of 0 is equal to 10, make that a bigger number. So then what that implies down here is that we would have 10 equals, and I guess the plus or minus c, we don't need to worry about too much now because we're going to find that c. equals e to the 0. Well, anything to the 0 power is 1, so that implies 10 equals c. So therefore, your particular solution here is 10 e to the x. Okay. Now, that's how you solve these particular points, plug it in. My one hint is going to be, when you do these, is solve for y first before plugging in the known value. It can get a bit tricky if you don't do this step. This helps hopefully eradicate some of the errors, okay? Now, I don't know if it would have worked here, because say we would have, I'm just thinking out loud, if we would have plugged it in here, we would have plugged it in sooner. By it, I mean f of 0 equals 10. Let's see if we get the same c value, c equals 10. So you'd have the natural log of 10 is equal to 0 plus c, which notice by using this one right here, you'd have the natural log of 10 is equal to c, which that is not the same as c equals 10. And that's my idea, and that's what I'm trying to tell you, is the hint is you have to get y by itself first, because sometimes solving for this constant c with the absolute values in the logs, it's not quite as simple. And I know that might not be rewarding for you to see why this is yet, but in more and more calculus that you'll take, you'll learn about why this is. But for now, I'm just saying solve for y first before plugging in a value, and then you'll get your c value correct. Okay. So yeah, this gets a little bit more complicated, which is a different lesson for another day. But there it is, solving differential equations for a particular solution where there's no longer going to be infinite many solutions. We can find that constant c. We can figure out which one it's going to be, but we have to know something about it, some known value, a known moment in time, which we were given. And then with that, assuming you solve for y first, you can plug that in and find your constant that makes that work. Now, I guess it's good that we check on both these that we got it right. So let me just check our answers really quick. Let's check. Y equals x squared plus 3. If we take the derivative of this side with respect to x, we'll get dy dx equals 2x, which is what the first one was. And this one here, if we check, we'll get dy dx is equal to 10 times the function itself, which is e to the x. And then 10 e to the x equals y, so thus dy dx equals y, which works. Okay, so there you have it. Which you can also see if we would have put in natural log of 10, well, I guess that wouldn't have changed anything, but anyway, I'll leave that for another video, or not even, I don't even think we cover it in this class. So there it is. Hope that helps. If you have any questions, make sure you reach out, come to office hours, or email or message me. All right, bye-bye.